Well, a very good afternoon and very warm welcome to this April Bite-Sized Corrosion series. My name is Vanessa Seeley-Fisher, and it's really my pleasure to host everyone today. In every session of Bite-Sized Corrosion, we try to look at a different aspect of corrosion-related information, and we try to break it down into interesting and informative, kind of palatable nuggets, as it were, hoping that you will leave us feeling that you've learned something new and leaving you eager to continue in your journey to understand a little bit more about corrosion. Today, we're starting a quick two-session series looking at stainless steels, and we've titled this Stainless and Beyond. Now, I'm acutely aware that not every engineer has had vast exposure to the variety of construction materials available, and it's our hope that during this short season, you will gain some valuable information about corrosion-resisting alloys, which you may be able to apply in your day-to-day life. And I'm absolutely thrilled to be able to welcome Ken Perel from Multi Alloys to the microphone with me today. Now, Ken has a wealth of experience and expertise, and I'm so honored that he's willing to share that with us. He's been at pains to remind me that stainless steel isn't just a name for a single material, and that corrosion of iron was what started the process of trying to find something to help make it less corrodable, if I can term it that. And it's actually only been just over 100, 110 years since it was discovered that you could add some chrome to steel and get a product which retains some of the properties of iron, which make it so functionally useful, but actually helped us by providing some corrosion resistance. And that's about where my knowledge of stainless steel stops. And I'm thrilled, Ken, that you are here to help me understand and increase my knowledge of stainless steels and hopefully that of our audience. Ken, I've heard terms 314, 306, I don't know, ferritic, please help us understand what steels are what and how we can make them work for us.
Thank you, Vanessa, for the introduction, and also thank you for inviting me to be part of the series. So a useful way to navigate the maze of stainless steels that are out there by means of what we refer to in the industry as this family tree. And as you can see in front of you, we make the distinction between those grades that we refer to as plain chromium grades. Remember that there has to be chromium present for us to even start calling it a stainless steel. So on the one side, on the left-hand side, we're speaking about the plain chromium grades, and on the right-hand side, we're speaking about the nickel-containing grades. So if we start off with the plain chromium grades, and we're looking firstly at the lowest branch on the left-hand side, we see that the martensitic grades are where we're going to start. These are hardenable and heat-treatable stainless steels. So by heat treatment, we form a martensitic structure, and hence the name. And in order to form that martensitic structure, we need to have a little bit of carbon in the material, but the amount may vary depending on the actual grade. The corrosion resistance of the martensitic family is in line with their chromium contents, and it might range from about 11% up to about 18%. Mechanical properties, and that will come from the heat treatment, combined with their corrosion resistance, is what provides the useful attributes of this family of alloys. And so you get grades and applications which will range from wanting wear resistance from the material, or keeping a sharper edge, such as for knives. And alternatively, you might be looking for high strength, like in valve spindles and pump shafts. So in summary, that's that branch of the stainless steel family, the martensitic branch. We move on then to the ferritic branch, which again are so called because of their microstructure. They have a certain structure to the grains, and hence the term ferritic stainless steels. Again, they rely primarily on their chromium content, for corrosion resistance. But the ferritic family have a very useful corrosion characteristic, and that is that they are immune to a form of corrosion known as stress corrosion cracking. That occurs in a chloride environment, so put the chloride in front, so refer to it as chloride stress corrosion cracking. Now, if there's chlorides present, there's also a risk of pitting corrosion taking place. And so grades have been developed which contain molybdenum, because the presence of molybdenum in any of the stainless steels helps increase corrosion resistance or pitting corrosion resistance specifically. And this is in line with a particular formula, which there's not a slide to show it, so I'm just going to quote it. But your pitting resistance equivalent, your PRE number, is measured by the percentage of chromium in the material, plus 3.3 times the percentage of molybdenum, plus 16 times the percentage of nitrogen in the material. And that's an empirical formula. So we can see the presence of molybdenum in a stainless steel has quite an effect on increasing resistance to pitting corrosion. So the ferritic stainless steels have useful corrosion characteristics, but a downfall would be their weldability. They don't retain the good strength after welding, and hence they will only be used in thinner sections where any welding that does take place would be much lighter, if we could refer to it in that way, rather than heavy welding passes. So that's from the plain chromium side of the family tree.
So if the tree now reflects a kind of chrome and nickel, I'm presuming that moving across the tree, we're going to be adding some nickel into our mix. Would that be correct?
That's absolutely right. So nickel is what is known as an austenite forming element. So nickel changes the structure from a ferritic structure to an austenitic structure, and you need about 8% nickel in the material for that to take place. But it does become more complicated than that. Depends on the other alloying elements that might be present. So we're not looking at a high nickel alloy content necessarily, but from about 8% upwards. The austenitic grades make up the bulk of the usage of stainless steels because they have very useful characteristics. The corrosion resistance is very useful for a wide range of applications. They can be used in cryogenic applications, and also they have very useful forming and machining characteristics. Their weldability is good, and hence they're useful. They're very utilitarian, and especially around the 304, 316 type compositions. Now, the problem with the 304, 316 type compositions is that they are very susceptible to chloride stress corrosion cracking. So remember, we said on the one hand, the ferritics were immune to it. On the other hand, the austenitics are susceptible to it. So alloy developers said, well, how can we get the benefit of both worlds? And they could do that by bringing from obscurity the so-called duplex stainless steels, which have a combined structure of ferrite and austenite. And I say bring it from obscurity because duplex stainless steels were actually developed a long time ago as well. But the steel making technology didn't allow for the other properties we want from materials, most notably your forming, welding behavior, etc., to be of a suitable standard for them to become widely accepted materials of construction. So in their early form, they were primarily just used as casting materials. But, it's only in perhaps the last 30 to 40 years that they've emerged as very useful materials of construction.
So that's quite interesting. Our audience who were with us on our last session of Bite-Sized Corrosion, we were talking about duplex and associating that with galvanizing. and where that refers to a galvanized structure with a coating on the top. So here we're still talking about two materials being used together, but within stainless steels, we're actually talking about us kind of combining these two sort of atomic structures, which is a little mind-bending.
Yeah, that's 100% right. And I think that before delving into the duplex branch, if I may, I would like to just come back to the family tree. Point out that on the nickel side, we've also got some alloys which are referred to as precipitation hardening alloys. And this is, the fifth branch. It's perhaps the Cinderella branch in the sense that it's not well known and not widely used, but yet it's the branch can perhaps offer the highest strength in the stainless steel range. And that is achieved by forming a precipitate in the material, and the whole technology associated with that, and that requires an additional heat treatment operation to develop that strength. So they also have moderate corrosion resistance, but as I mentioned, their usefulness stems from their strength and also their toughness. So it's not strength with brittleness, but strength with toughness.
Well, I'm sure like duplexes have been brought to the fore more recently. Maybe they'll also have their day coming up sometime. But let's go back, if we may, to the duplex steels, because that's actually something that I think is quite interesting. They are known for their strength. And how would you choose a duplex steel for a project?
Right. So I think we need to work through this, and certainly the strength of the duplex stainless steels is a feature and which has made them extremely useful material construction over recent times. Now, in terms of what advantages can we get from the strength, the first thing is that it's not strength resulting from a separate heat treatment operation like you have with the martensitics or the precipitation hardenings. It's really the inherent strength of the material from the manufacturing process. It comes about from the structure on the one hand, but also the alloying elements that are present in the material to start off with. And so you have a material which in its annealed condition, which is in its as supplied condition, in its annealed condition, you have a material which will have at least double the yield strength of your common austenitics, of your 304s, 316s. So with double the yield strength, you can appreciate that you have some advantages, particularly if you're not sacrificing corrosion resistance anywhere along the way. You have even bigger advantages if the corrosion resistance is increased. So what would be the benefits, from the strength? Well, where these alloys have started coming to the fore, for example, has been in the construction of large tanks. So instead of considering a structural steel, a carbon steel, and having to apply a coating system, or having to use an austenitic stainless steel like a 304, 316, but then having to use a thicker section because of its limited yield strength. So the duplexes have come to the fore in that sort of way. A second benefit, and that manifests itself in a life cycle cost type calculation. A second benefit is that when it comes to being able to cope with operating stresses. So, for example, if you have rotating equipment and you have high stress being opposed while the equipment is rotating, very often you would be outside the approved limits for an austenitic material. Whereas with a duplex material, the chances are you might be within the design limits for the material. So that's another advantage. And furthermore, you might be able to down gauge the thickness of material. So that would mean that your drive system and everything that goes with it could be specified accordingly. And a third example that I'd just like to quote is when it comes to pressure-bearing piping. You could perhaps reduce the wall thickness of that piping and still be able to withstand the necessary pressures. And the derived benefit from that could well be that if you're speaking about heat exchanger tubing, where you're relying on thermal transfer, the thinner you go with wall thickness, the better it is from a thermal transfer point of view. So again, there's a bit of benefit that comes from that. So you can get a feeling for some of the applications where that might arise from the duplex stainless steel having the properties they do: corrosion resistance, resistance to stress corrosion, cracking, and strength.
That's almost like the perfect steel that you've described. If it resists corrosion and we can use less of it, so it costs less, and all of those attributes, I'm going to have to ask you, what are the drawbacks?
Well, we haven't fully exploited the corrosion resistance, but in terms of drawbacks, certainly the metallurgy of duplex stainless steels is more complex. And as a result of that, there are some limitations in terms of the temperatures that they can be used at. And around the 300 degrees centigrade mark is the limitation for temperature. You wouldn't be able to go up above that without a changing structure and perhaps becoming embrittled or affecting the corrosion resistance of those temperatures. So I think that's perhaps the most significant drawback I can mention.
Ken, what about fabrication challenges, welding issues? I know one of the challenges that are often raised from a site perspective is, but it's too difficult to weld. Or is that something that we also experience with duplex stainless steels?
So again, I think let's just start by benchmarking against the 304, 316 materials, which are the workhorses in the austenitic range, which most people might be familiar with. So if we benchmark against that to start off with, I think what I can say is that the welding and fabrication is different, but not more difficult. Let's start off with that in mind. Different, but not more difficult. The strengths of the duplex material, because they have the high strength, certainly your equipment, your bending equipment, your fabrication, your cutting equipment, wouldn't be able to tackle the same sort of thickness, the duplex grade, as maybe you can do with your 304s, 316s. When it comes to machining, you would have to change your machining parameters, because you would have to probably apply greater forces during the machining operation. So one needs to bear that in mind. Another thing is, because of the more complicated metallurgy, the material cannot be stress relieved as you would a structural material. So that needs to be taken into account. And similarly, hot forming needs to be done in somewhat different way.
I think your phrase of different, but not necessarily more difficult, is worth bearing in mind, because I think as a community, we tend to go as different, therefore it's difficult. And you're saying it's not difficult, we just need to change our mindset. So I'm assuming that will apply to welding as well, is that it's different, but maybe not more difficult.
That's correct. I think the situation is that, if one is using a duplex stainless steel, one's got to recognize it's a duplex stainless steel, and it's not an austenitic. It's not your 304s, 316s, which people might be more familiar with in an operating environment.
Right.
I think we should just point out that there's three branches on the duplex stainless steel range: what we refer to as lean, standard, and super. And they go up in corrosion resistance in that order. They've all been developed as materials of construction which should be weldable. So welding has been taken into account, from the outset to make them useful material. But yes, it does mean that there still remains a risk of deleterious phases, damaging phases forming in the material. And that means the welding operation needs to recognize that you need to balance heat input. And that can be done by, amongst other things, managing your welding speed, filament metal selection, diameter, interpass temperatures, etc. And of course, the most appropriate filament metal needs to be chosen from the outset.
Well, that makes sense. if we can just go back very briefly, I glossed over corrosion resistance because they are duplex and because they are corrosion resistant. But I'm sure within those three branches, and even within that, I'm guessing that it'll be changes in composition maybe, or quantities of, I don't know, some magic metal that you're not going to tell me, which will give different amounts of corrosion resistance or different corrosion resistance in certain scenarios?
Yes, absolutely. So, I mean, if we look at it, you can see on the lean side, it's leaning more towards the plain chromium side. So, what the term lean refers to is that it's lean in nickel. So, the duplex structure, in other words, getting the austenite into a lean duplex stainless steel is achieved by the use of manganese and nitrogen. So, hence the term lean duplex. And its corrosion resistance is in line with that. The corrosion resistance is quite adequate for many, many applications, and they become useful materials. The standard duplex, on the other hand, is a grade that we know with the general terminology of 2205. It's referred to as standard duplex stainless steel. So nominally it's 22 chrome, 5 nickel. There's some molybdenum and nitrogen added as well. So again, that molybdenum and nitrogen and chromium present will give you your fitting and crevice corrosion resistance. And again, its corrosion resistance will come about from the alloys that are alloying elements that are there. And then as we move to the right-hand side, we've got the so-called super duplexes, which have even more chromium, nickel, and molybdenum, nitrogen, etc. As you increase what we refer to as the austenite formers, which is your nickel and nitrogen, so you can increase your ferrite formers, which are your chrome, molybdenum combination. So I think that's in summary. And as you're increasing those alloying elements, so you'll increase corrosion resistance, most particularly your pitting corrosion, your crevice corrosion, and your stress corrosion cracking resistance.
Right. So they really do start to become super duper, if I can use that term. That has been so interesting. Thank you. And I definitely feel like I understand them a little bit more. Just as we close, Ken, I don't know if you've got any last few comments that you'd like to add about duplexes. Are we still growing duplexes? Do they still make new ones?
So yes, I mean, as a group, these alloys continue to receive attention, and as recently last month, there was an industry trade announcement of a new grade being developed, specifically targeting applications in the offshore industry. So these are not things we would tend to see necessarily in this country and maybe up, on the inland of this country. But there are useful materials, and this new grade in particular offers a combination of strength, corrosion resistance, and from that comes you get safety and you get reliability coming from that, which you need in the offshore industry. So ultimately, the grade might manifest itself as well in heat exchanger applications, etc. That's fairly recent.
That's so interesting. I can see that this is a topic which has a number of side roads which are probably worth exploring, and we'll have to make time sometime in the future. Just a quick question that's come in from the floor. Are duplex stainless steels manufactured here in South Africa, or are they all imported?
Can I start off in a long way, if I might? That is to say that in South Africa, we do manufacture flat stainless steel products. So sheet and plate stainless steel is manufactured here, but we don't really manufacture much in the way of piping. I think we do have tubing, which is used in the automotive industry and other applications. And we do, and that's all welded tubing, and we don't have any bar manufacture here in South Africa. So coming back to the question, do we manufacture? So certainly yes, on the duplex stainless steel plate side, 2205, the workhorse grade is made locally, and then there's also, I think, the lean duplex made locally. One of the things about the lean duplexes is that there are several grades under that banner, and similarly there are several grades under the super duplex banner. So the demand for product thickness, logistics, supply chains, etc., becomes more complicated to justify big tonnage melts.
Super. Well, thank you. And thank you very much, Ken, for a really fascinating discussion. And to carry on this next week, I'm going to invite our audience to join us next week on Tuesday as we chat with Ken about adding a lot more nickel to the mix and see what happens then. And in the interim, have a wonderful week, and we look forward to seeing you soon. Take care. Thank you for joining us.